But let me start by showing you some insights of a retrospective review we've made recently on more than 700,000 screens collected from different sites in the United States. And from those screens, radiologists have identified around 4,000 cancers. But we didn't look at the screen that the radiologists found the cancer on. We looked at the prior screen 1 year before, 2 years before, and 3 years before. And we asked experts to see if the cancer was already visible in those screens before. And what we found out is that 30% of the cancer were already visible 1 year before discovery, 12% 2 years before, and 5% 3 years before. What does it tell us? It tells us basically that, first of all, finding cancer is a very hard thing to do for radiologists, need a lot of expertise, but also that there's a lot of room for improvement and that AI can certainly play a big role in all that. Well, developing an AI for breast cancer screening is, of course, and we know that, a very difficult topic. The first thing to consider is that the cancer, fortunately, is a rare event. So you need to collect a lot of data from multiple sites to create a data set which is sufficient to train your models. But by doing that, you will start to introduce a little bit of biases in your model, but I'll come back to that later. The next very important point to consider is the fact that curation, the process of looking at the data and making sure the data is clean, annotated, is something that takes a lot of time. I put here an example of lesion identification inside a tomosynthesis, where you can see that a mass can be visible across all slices of the DBT, yet you would like the AI to refocus its attention where it's the most conspicuous, where it's the most visible. So you ask radiologists to contour findings precisely in the slices you would like the AI to find them. And in light of what I've just shown before, you want to also make sure that the cancer-free screens are actually cancer-free. And a lot of rules says, okay, maybe you can take a 12-month negative follow-up to say that a cancer is not present in this image. Yet, in light of what I've shown, we should probably push back this limit to up to 3 years to really make sure the data is clean enough to train your model. And one thing also, sometimes which is not clear to everyone, is that most of the data you use is actually non-informative. Basically, 90% of the data that we collect is almost useless. It's simple, benign, normal cases that doesn't bring a lot of information to your model, while there is a limited set of 10% of very difficult informative cases, which are, of course, the cancer case, but also the hard, what we call the hard benigns. So basically the cases where the radiologist had a very hard time telling if it's benign or malignant and needed to go through workups. So the question we raised when we developed this new AI is how can we leverage most of the data in an efficient manner? And this is how was born a new model, we called it HydraNet. So HydraNet basically consists of a structure called the backbone that will extract a lot of features from images, and it needs to be representative of all the diversity of breast tissues it can see in reality. Different densities, different type of lesions, artifacts as well, different ethnicities and so on. So you want the backbone to be the most complete and have a really good understanding of what breast tissue is. And then you get the neck, which is what we call a multi-scale feature extractor. It gives the model the capacity to look at the neighborhood and the contextual information around the lesion. Take this example of a small mass which is in between the pectoral muscle and the glandular area, which is worrisome in some point because it's a region where you don't want to see masses. And the same mass which is next to the nipple, for instance. Well, in one case, you would like to model to understand that it's more worrisome to see a mass there than next to the nipple. And this neck gives really the capacity of the model to learn this type of features. And then you get the heads of the HydraNet, which serve different objectives. So one of the objectives, of course, is to predict the probability of malignancy for the image. But not only one image, you have one head that works also with a symmetric image. So it takes one image, it's symmetric, and see if it can predict a better probability of malignancy. And then we have something we call the prior heads, which take an image and its prior image 2 to 3 years before to determine the level of malignancy as well. And then you can have heads that work on, that will determine the type of the lesion, is it a mass, distortion, calcification, so on, and also the position of the lesion. Now, how you train the beast? How do you train that big hydronet. So first of all, as I said before, the backbone is really what creates a lot of structure and a very strong representation of what normal breast tissue is. And you want to use as many data as you can. You want your backbone to look at a lot of data, regardless of whether it's benign or malignant. So you discard the notion of labels. And naturally, you end up trying self-supervised learning technique, SSL techniques, which are something relatively recent in the field, in the medical image world. And I try to pass the notion intuitively, but basically how it works, you crop a patch in an image, you perturbate it, you rotate it, you shuffle it a little bit, and you tell to the model this patch and its perturbated version is more or less the same thing. And by showing a lot of those patches, sampling and doing a lot of perturbations, that helps the backbone to build itself this very strong representation of features that will serve for training the heads of the hydronet. Now, when you look at the training of the head, the neck, and the heads, and I'm going to take the example of the head that will predict the malignancy of a case, you want to sample your negative in a very smart manner. And you don't want to overwhelm your model with lots of negative cases which are non-informative. You want them to be much more accurate. And so on the left, you get a sampling of the negative, which is randomly made, and on the right, something we call hard benign sampling. So there's not much difference between the two a priori. The ratio between the blue bars, which are the benign cases, and the orange bar, which are the malignant ones, looks more or less the same across both types of sampling. But when you look at the details, you can see that on the left, the green bars are actually the simple benigns, so the true negatives. It means that in that sampling, we show a lot of simple things to the model, lots of radiologist true negatives. While you can see that the blue ones and the orange ones, which are the radiologists false positives, and radiologists false positive which have been biopsied, are very few. You don't have a lot, so you don't show a lot of complex examples to your model. While on the right, by tweaking the way we sample data, you can put as many radiologists false positive as radiologists true negative. So you oversample the hard benign cases, and that really helps the model to understand and separate better what's benign from what's malignant. Another type of sampling we've made as well, we call it natural sampling, is something to counter the bias that you introduce when you collect data from multiple sites. Take these very simple examples. Imagine you collect data from a site which contains only negative cases. For reasons, you could not collect any positive case from that center. You're going to inject this data into your training data set, you're going to train your model, and what happens? What's going to happen is that your model will start learning that this data comes from this center, and given that there is no cancer from that center, it will automatically reduce its level of suspicion on the case, which is a very bad property, right? You don't want your model to think that because the data comes from this center, there's no cancer at all. And deep learning is very good at learning those kind of biases. So to counter that, we developed a methodology that will sample every site, every source, proportionally to the number of malignant positive cases it brings in the whole data set. And doing that helps the model to unlearn this type of biases and converge better. And finally, we've made some combination between 2D and 3D. 3D tomosynthesis is very good, yet it's not bulletproof. Sometimes you like the 2D image, notably for classifications, because they're more visible, they're more conspicuous, and sometimes they're too hard to find on DVDs. While on DVDs, it's the opposite. Distortions are better, and they're more conspicuous. So here, we just give the model a very simple heuristics, which states that if you find the same finding in 2D and 3D at the same position, you can transpose it to the combined mode, where 2D and 3D are fused together, and you inherit from the maximum malignancy score of both detections, in that case, the 3D. And if you see a detection only in 2D or only in 3D, you can just port it back to the combination of the two. So you end up with 2 detections in 2D and 2 detections in 3D, to 3 detections only in the combined mode. And that helps the model to basically understand the combination, the correlation between 2D and 3D, and give superpower. Well, just to talk about results now very rapidly, using all the methodology we have developed, we end up with a gain in all metrics. And notably, we don't miss any screen-detectable cancer for a 50% level of specificity. This was evaluated on more than 700,000 screens. Just an example of a case, sorry it's in French, where a lesion was missed by the radiologist, but I could spot it rapidly. Thank you very much for your attention. I hope you enjoyed this presentation. If you want to know more about HydroNet and all the development we've made at Therapixel, we are just there. And I encourage you also to assist to the talk of Serena Pachile, our clinical research director, who's going to present the result of his retrospective review of more than 700,000 cases. Thank you very much.